not familiar, one of the claims, and correct me if I'm wrong, is that we could conceptually have a, let's say, the set of all positive even integers, 2, 4, 6, 8, and so on. And we can say all of them. So we take every single one and we put them into some upper boundary on it, and we're talking about all of them. So if you do that, if you play by this widely, you can say, okay, how many elements are in this set? Most infinite amount of numbers. But then you say, okay, now imagine a set of all the positive even and odd integers, 1, 2, 3, 4, 5, and so on. It seems like there would be more elements in that set. Intuitively, you think, of course, there are new numbers in this set that there weren't in that set. And yet the conclusion is they actually contain the same amount of elements. Is that correct?
Well, I think a mathematician wouldn't say it that way because we don't want to talk about the number of elements, when we're talking about so-called infinite sets. Right? You have to understand, I don't really believe in infinite sets, so, I have to take on the position of authority here in defending it. So they would say, okay, we're not allowed to talk about the number of elements in infinite sets, but what we can do is we can talk about the making a correspondence between the number of elements in this set and the number of elements in this set. So if you kind of match them up, one boy for every girl, then that's some kind of reasonable replacement of the idea that they have the same number of elements. We may not be able to tell them, but we can see that we can match them up. So that's the way the modern mathematician would want to rephrase that argument.
Okay. Now, is that kind of a humanistic way of rephrasing it, or is that an incorrect way of thinking of what infinite set would imply? That that, for example, the concept of cardinality is really talking about the number of elements in the set. So is it a mistake to think of cardinality in the same way that we think of it applied to finite things when we apply the same set?
I wouldn't say it's a mistake, but I think you have to be very careful. And it's easy to distort things by using the language of finite things, with the intuition that we have for finite things, and trying to apply them to the so-called infinite situation. I think it was Hermann Weyl, I think it's Hermann Weyl, who said something about the lines of that this is one of the weaknesses of the modern approach for set theory, that we try to invoke the same arguments for the infinite case as we do for the finite case, but the laws of logic are really different. But from my point of view, it's actually much more simple-minded in the sense that I believe in writing things down. I have a very computational point of view, and not a very philosophical point of view, in fact. So maybe I'm a little bit naive from a philosophical point of view. So for me, a mathematical object is specified when you write it down, and that's really necessary. So one can have fancy thoughts and so on. That's great, but ultimately, if I want to convey an object, the idea of an object to you, I'm obligated to write it down. And that's really the problem with thinking about infinite sets. That we can say things like the set 1, 2, 3, 4, and so on, but you can't actually express that set. Okay. But that problem emerges long before we get to infinite sets. It even starts appearing when we get to very large sets. Maybe this isn't appreciated as much as it could be, but the difficulties with set theory are not just at the infinite level, they're also at a very big level. Once we get to the idea of numbers that are so big that we need some kind of towers of exponential kind of notation to get at them, then we're already in a realm where a lot of our arguments break down. In other words, there are limits to computation. There are limits to what computers can do, and not because our technology is necessarily limited, or because we're not smart enough yet, we haven't built enough machine. It's just because the universe is organized in such a way that there seems to be some smallest limit to how much you can compress space, how you can subdivide space. Like there's a Planck scale sort of limit to how small you can compress, and there seems to be some large-scale limit to how big the universe is. So if you put those two together, it means that there's really only a finite number of possibilities that are inherent in the world in which we live. And you can quantify that, at least like you make some estimates that physicists can give you, and you can quantify and see that once you reach numbers that are of the order of 10 to the 10 to the 10 to the 10 to the 10, something like that, then you're talking about numbers which now no longer can represent real collections in our world, no matter how small you've created them.
Now you say that's not a philosophical position, that is very much a philosophical position. You're saying that numbers don't exist really outside of our conception of them, we're outside of us writing them down. Is that fair to say?
Let's say that's my position. Okay. So my position is I'm a down-to-earth person. I want to see things written down. To me, that's the litmus test of whether something is real or not. You may have all kinds of ideas, but until you can express them in some kind of way that we can all look at them and compare notes and really study them, then to me it's some kind of abstract level.
Would you say this is my position as well? Would you say that it is true that numbers don't exist, separate they're being conceived, that formula that necessarily entails a kind of logical finiteism that you can't get to infinity if all the objects you're talking about must be objects of your conception that you can't conceive of infinity?
See, I guess I would rather not even discuss existence. See, to me that's a philosophical question, the question of whether ghosts exist or angels exist and so on. I don't know. It's a philosophical question. I'm a mathematician, and I'm very concrete and down to earth. So the question for me is, what can we write down? What can we compute? What formulas can we come up with that we can take the left-hand side, we can take the right-hand side, and we can verify that the left-hand side equals the right-hand side?
So you're agnostic for the other side?
Yeah, I'm agnostic. I'm uncertain as to what the word exist really means. To me, the relevant thing is what can one write down.
Right. Okay. So for anybody that's not familiar with some of the claims about insensitivity, I think it's helpful. I remember watching a video of yours where you gave an example to the audience about some of the counterintuitive conclusions about whether or not you can actually communicate the process, or I believe you gave something like, there are an infinite number of balls over here, and take a ball over here, if you know what I'm talking about. So if there are what are some examples of where you get profoundly counterintuitive conclusions when you try to actually complete sensitivity?
There are quite a lot of them in modern mathematics. There's quite a lot of unintuitive results that people believe are true, and they're really dependent on prior belief system with respect to real numbers and infinite. One thing mentioned the Monod-Tarski paradox is you're probably familiar with. It's a well-known sort of assessment that you can take out all of the sides and rearrange it into a finite number of pieces, maybe 5 or 6, and then rearrange those same pieces, move them around, and rearrange them to get a solid ball exactly twice the size, let's say. There's things like non-measurable sets, non-measurable functions, which in modern mathematics are somewhat unintuitive, counterintuitive. There are things like space-filling curves that ostensibly go through every point in a square in a plane. But I think those are all in some sense sort of peripheral and ultimately really rather unimportant, because they're results with no consequences. They're sort of gee whiz and very interesting things, but they're completely devoid of consequences because the mathematics behind them invokes these things that you actually cannot do computationally. They're sort of hidden behind the things. Although I think a much better and more interesting example is a belief that most mathematicians have, that I think most lay people would find rather astounding. And this actually is a belief that actually has a lot of core implications. So if we look at the interval from 0 to 1, okay, and we think about the numbers in there as infinite decimals. So we have to convert from a dedicated quadratic sequence to infinite decimals, but they're largely equivalent. So imagine infinite decimals between 0 and 1 for a second. And there's this really fundamental dichotomy that was pointed out strongly by Wittgenstein. He was always sort of one of the leading philosophers of the 20th century, not the leading philosopher, most influential. And he said, look, there's a very fundamental distinction between two kinds of infinite decimals. On the one kind, you can think about an algorithmically defined infinite decimal, one that's generated by a computer program, or maybe a function or some kind of algorithm. And on the other hand, there are, or at least one is potentially able to think about sequences which are not generated by a finite process, for which you might imagine some kind of oracle. They've got another universe that has an infinite brain and an infinite time. And this oracle just spews out digits for this infinite decimal, but without any prior finite algorithm or pattern. So on the one hand, we have these sort of algorithmic decimals, and on the other hand, we have the infinite choice decimals, they might say. Okay. Now, if you actually look in the real world, when you make an integral, or when you compute an arc length of a curve, or you get some infinite sum, or you do one of the many things that mathematicians actually do involving some infinite process. If you do believe and you allow them to get some results, you will always get one of these first kind of infinite decimals. They're not necessarily algorithmic decimals. But the belief system that modern mathematicians almost universally share is that most of the numbers in interval 0, 1 are actually not of the algorithmic kind. They are this infinite choice kind. Which means that in fact, the numbers that we use actually in practice are a minuscule fraction. In fact, measure zero is the terminology that's used. So the measure zero subset of all of the real numbers. So this is a kind of fantastical belief system, really, that most of the numbers that are actually there are ones that are completely inaccessible to us and our machines.
Now, can you give the devil's advocate from your perspective? Because from outside the profession, that seems merciful. Well, can you even reference these numbers? Are they literally just like behind the veil that we can never even access that are out there? What is the justification for that kind of position?
Well, so the terminology that we use are computable numbers and uncomputable. So the algorithmic ones are the computable numbers, and the other ones are uncomputable. And the claim is that most numbers are uncomputable. Most in a very strong sense, in the sense that the measure of the computable numbers is 0, the measure of the uncomputable numbers is 1, in the interval from 0 to 1. If you want to forced to buy all these uncomputable real numbers, so they come as a package. So it's an unpleasant situation, and people go to shrug their shoulders and say, well, let's just carry on.
From my perspective, that position strikes me as eminently philosophic, in the sense that what it seems like the modern mathematical orthodoxy is claiming is that mathematical Platonism is true, that there exist these numbers that are out there that are inaccessible and incomputable, and we can engage with them in some kind of limited fashion. But does that not require a very strict metaphysical claim that there exist these numbers
that are out there that can be conceived. I think you're right, but I think that's correct. I think it is highly idealistic. I think it is highly philosophical. In fact, in my view, 20th century mathematics really does have a strong philosophical foundation. I mean, the foundations of set theory and logic that were introduced in the early part of the 20th century really are coming from classical logic and philosophical side of mathematics. And that's really dominated the thinking, at least in a sort of formal sense. It's like going to church once a year. Mathematicians will say they believe in this theory, but they say it's just to keep people happy, and they don't actually really effectively use it. But it's a kind of it's a justification, it's a framework that will allow them to continue this belief in these real numbers and these basically being able to calculate the curve systems. Okay, so let me ask you a couple of short questions. When talking with people who have some kind of training in mathematics, or people who don't have training in mathematics, actually having a conversation for 10 years about this, they said, Steve, how can you claim that there's no such thing as these completed infinities and infinities? Because in calculus, for example, completed infinities all the time. Central to calculus is this idea of the completed infinity, or conceiving of how it doesn't work. So how do you respond to something like that, that if you don't have the completed infinity, well, you've just undercut a huge amount of mathematical thinking? Well, I guess you do undercut a lot of current thinking, but this thinking has not always been this way. So in the course of the last 3 or 4 centuries, since the 17th century revolution, there has been quite a wide range of opinions and thoughts in this direction. So the current belief system is not really representative of the historical record. You must appreciate that the way we think now is as a 20th century construction that would have been very alien to 19th, 18th, and 17th century mathematicians, even though it may be almost universal these days. But in earlier times, people did think about calculus problems and how to resolve them. They didn't realize there were issues, and there was a lot of discussion on that. They were resolved entirely. But just prior to the 19th century, I think Euler and Lagrange were on a very positive direction. They had mapped out a direction that was leading to a more algebraic approach to things. And I think this is really where the potential for the future lies, is to go back to the Euler and Lagrange, who probably understood calculus better than anybody has before or since, and really build on their thinking. And it's possible to do that, and it's possible, I think, to go quite a long ways, but we need kind of a more diverse pool of people thinking about other ways of thinking, other alternatives to the limit-based orientation that we have now, which is basically a 19th century invention. So do you think it would be a mistake to think that calculus can work, or that there's no way of conceiving of an effective way of doing calculus without including the actual infinity? So that's a very big mistake. In fact, I hope in my YouTube channel to, in the next year or two, to create a course on algebraic calculus, and to demonstrate that, in fact, one can do calculus in a completely cut-and-dried, right-downable fashion. So I hope to demonstrate this so directly that these things are possible. Okay, now what about something like geometry? Because at least from the outside, it seems like infinity also comes up in geometry. Is that something where you say, you really don't need any kind of infinities in geometry either? Yeah, you don't need infinities in geometry. You can get around that. I mean, it's not that you don't want to talk about things, that one might say are infinite or infinitely far or something. It's simply you have to find a way of doing it in a finite, right-downable way. And people have wrestled with that in projective geometry. So projective geometry, one introduces points which are infinity. And formerly that was considered rather mysterious, looking at points that are infinitely far away, and so on. But in the 19th century, people like Mobius and Hooker started to understand really how to do this in a very concrete, beautiful way, without any resorting to infinite processes. So looking at things, there are alternate ways of doing things that allow us to get at infinities, but in a finite, concrete, beautiful way. So let me add, right, that ultimately our computers, what our computers do is sort of almost by definition finite mathematics. So you can get a computer to do something. It's almost necessarily based on ultimately finite thinking, because that's what a computer is. Right? And so computers are known to be very good at calculating lots of interesting things, so I think they're going to become increasingly important in the decades to come, even in terms of doing pure mathematics. And we're going to see that their limited, seemingly limited infinity point of view will ultimately swamp our philosophical current approach. So are there areas of mathematics which can be rescued? Is it true that this idea of complete infinity is a bit wonky? Are there areas which that really does fundamentally displace? Look, I think a lot of them keep pace to a certain extent, but I wouldn't go so far as to say they can't be rescued. I think every subject can be rescued, it can be rebuilt, and can be restructured, rethought. I think it's a huge challenge that awaits 21st century mathematicians to really get down, roll up the sleeves, and really get down to the foundations and figure out how to do these things. So even modern set theory, I believe that what they're doing is not just in rescue, that there really is content there, but that they have to find some way of saying what that content is in a way that's concrete and finite and computable. So, from your perspective, this finiteness perspective is very much a minority, especially in the modern world. In my own discussions, in my own fundamental understanding of mathematics,
I get a lot of flack for people who haven't produced nearly as much content as you have, just a fraction of the pressure. I get a lot of flack for people who say, you can't get rid of the 10 days of mathematics. You're just a crank because this has been settled 100 years ago. How do you respond to that? I mean, obviously, you're in the process of creating a ton of binary mathematics that is very powerful, and it can be understood without resorting to these grandiose stories and abstractions about infinity. Do you think that there is in the mathematics profession, do you think that there is a kind of, maybe dogmatism is too strong a word, do you think that there is an overconfidence, let's put it that way, in not establishing these foundational issues before going into your craft? So, a more concrete situation. Somebody who goes through the mathematics education, either PhD, I think it's a system, are they going to be grounded in sound foundational reasoning about the subject matter? Or is that kind of overlooked to do the more interesting? Just assume this is all correct foundational stuff, and we do that interesting craft. Sure, that's certainly true. Yeah, absolutely. I mean, the foundational problems are deep problems. There's a whole range of concepts which are not really spelled out clearly. Most of the elementary words in mathematics, from function to sequence to number to set, these are just used loosely and kind of intuitively, and everyone kind of agrees that we kind of know what a function is. We don't really have to spend a lot of time and effort saying exactly what we're talking about. And if we do say exactly what we're talking about, we tend to use the same synonyms. We play kind of a circular game. A function is a rule, and a rule is a process is a function, that kind of thing. But look, I think that the modern PhD has been. We are elements of our culture. I have been too. We are taught along the lines of the correct orthodoxy. It's important, and I think the great maybe your channel and your podcast are doing this kind of thing, of enlarging people's views, of showing them possibilities that yes, there's an orthodoxy, but maybe it's not the whole story. Maybe it's not even the best part of the story. And certainly my investigations in the last dozen years ago, so I developed this thing called rational trigonometry some 10, 12 years ago, and I used that to reconfigure hyperbolic jump. The foundational difficulties that are encoded in the imprecision of the way we use words means that a lot of mathematicians can't really get up close to the things that they're essentially studying. Like you can't really get a real number, for example. You can't actually possess an infinite decimal. So you end up saying things like, let alpha be a real number. Okay, that's different from let alpha be a decimal with eight digits. That I can assume it. I can get right up close and we can all have a look at it. But if you say let alpha be a real number, then there's a